Welcome. My name is Lutz Warnke, and for this recording, I'm stepping in for my co-author Sileikis from the Czech Academy of Sciences. And today I want to discuss a problem which is well understood from the perspective of random graph theory, but if one views it through the lens of extreme value theory, there's still some very interesting open problems, and I hope to get some of you interested in working on this. So what is the model that we're looking at in this talk? So we're going to look at the classical Erdős-Rényi or binomial random graph GNP. So we have a graph with n vertices, and each of the n choose two possible edges is inserted independently with probability p. This is a very classical, well-understood random graph model. So what are the objects of interest that we're going to study? So we're going to study some kind of local statistics. And so the simplest local statistic is, for some vertex, how many edges are adjacent to it, how many neighboring vertices are there. This is usually called the degree. And once we ask how many edges are adjacent to some vertex v, then you can also ask how many other structures are adjacent to some vertex v. You might be interested how many 4 cycles are there adjacent to some vertex, or how many 4 cliques, complete 4 vertex graphs are adjacent to the vertex. And you can generalize this now. For example, you can also ask, given 2 vertices, how many paths of a certain length are there, and so on and so forth. So I hope you get the idea. These are the kind of local statistics we're interested in. How many ways are there to extend a certain vertices to a certain structure? And the classical perspective that is very useful in random graph theories, I would say, is the concentration perspective. So we want to ensure that, for example, every vertex has approximately the same degree, or in general that every pair of vertices is, say, in the same number of paths, and so on and so forth. So this is some kind of concentration view. We want, no matter where we look, things can be extended in the same number of ways. And I think it's fair to say that for this kind of perspective, we nowadays have a very good understanding of what's going on. In particular, this paper by Joel Spencer from 1990 gives some very good sufficient conditions. When is it true that at every vertex I have the right number of extensions? And last year, Sileikis and myself, we revisited this problem and added some more details to the understanding of this problem. In this talk, I really want to point out that besides the concentration perspective, there's also this extreme value perspective. So whereas in the concentration perspective, we're saying we want this roughly the same number of extension counts at every vertex and so on and so forth. Now here we're going to ask, what is the maximum possible number of extensions that are there on some vertex or a set of vertices? Okay, so for example, for the degree, what is the maximum degree in the graph? So we want to find the vertex which maximizes the degree, and we want to understand how large is this degree. Or similarly, for the 3 vertex count, we want to say, okay, what is the maximum number of 3 vertex paths that sit on any 2 vertices? And perhaps surprisingly, although this problem is extremely natural, not so much is known about it. So most of the things we know, they really come from the concentration perspective, and I think it's really understudied from the extreme value perspective. So there's really a lot of room for bringing in tools and techniques that are well known in the extreme value theory realm to bring them here to the area of random graphs. And I think it would be really nice to see some new contributions here. Let me advertise this a little bit more. So let's first do a quick case study. So let's revisit these degrees in a binomial random graph. So we're interested in the degree, how many vertex edges are there adjacent to some fixed vertex v. We're going to note this by d of v. So note that once we fix a vertex, the number of adjacent edges, that's just a binomial distribution where we have n minus 1 possible neighbors. Each of them is included independently with probability p. So it's very simple to calculate things like the expected value or the variance and so on and so forth. So on first sight, it seems that this is an easy problem. However, keep in mind that when we look at this entire vector, which contains the degree for each vertex, then there are some slight dependencies here, okay? So this vector is not just independent binomials, but there are some slight dependencies simply because, look, once we know all the neighbors of the vertex v, then we already know whether, for example, this edge here is present or not, which has some influence potentially on the degree of w, okay? So while the vector is not completely independent, I would say it's fair to say that the dependencies are fairly weak, because for every pair of vertices, for example, they share at most the status of this one edge. Okay, so these degrees, this is a very, very, very classical thing and has been studied since the early days of random graphs, of course, because it's a very natural graph theoretic parameter. And so from the concentration perspective, we want really that all the degrees are approximately the same. So one way to say this is to say, okay, for any epsilon, I'm interested in when is it true that all the degrees are close to the expected value. In other words, when is it true that if I subtract off from each degree the mean, okay, when is that always less or equal than epsilon times the expected value for all vertices? Okay, this is what this is saying. And it turns out that the simple sufficient condition, which is also essentially best possible, is if the expected value is much bigger than log n. Okay, how do you get such a result? Well, you do a union bound over all vertices. So what's the probability that this is violated? Well, it's the probability that this is violated at some vertex. And then we can use Chernoff bounds to understand what's the probability that this fails at one vertex. And if you do this, you see that exactly you want that the expectation is sufficiently large. And I should say that here and elsewhere in the talk, I'm ignoring kind of the case when the probability is very, very close to 1. This is a degenerate case, which I do not want to discuss here. Okay, so the concentration perspective, all degrees are roughly the same. And the extreme value perspective now asks, so what about the largest degree? Note that the concentration perspective already gives you some information about this, because the concentration result basically tells you if you look at the maximum degree, and the maximum degree of all vertices, you renormalize by the expected value, that this converges in probability to 1 if the expectation is much bigger than log n. And if you now, of course, you can ask, okay, I want much, much finer knowledge about this random variable. So what I should do is I should not divide by the expectation, but subtract off the expectation. Right? So this is what we do here. We look at the maximum over all degrees minus the expectation of a vertex, and then we renormalize here. And this old result by Bolobash tells you if we normalize by square root of 2 times the variance times log n, then this converges to 1 in probability. If basically the variance is at least some power of log. And in fact, the result tells you much more, that the fluctuations are asymptotically gumball. So there's some nice distributional information as well. And now, as you can guess, we now can ask the same kind of questions for these extension counts. It's kind of like the local statistics beyond degrees. Remember, the extension counts for things like, oh, how many cycles are contained in some vertex? How many clicks, complete 4 vertex graphs contains a vertex, and so on and so forth. And believe me, there's some way to generalize this, where instead of looking at these 4 cycles, 4 clicks, 3 paths, you look at some general copies of some graph H. And instead of 1 or 2 vertices, you look at some set of vertices R. I'll postpone precise definitions to the paper, but I hope you see that something like this should be possible. And the concentration perspective now tells you that, okay, our goal is to ensure that all extension counts are the same. So similar to degrees, now we want that for any possible choice of the roots R, we want to get the correct number of extensions. And Spencer has here a very nice result from 1990. He basically says that, okay, if you're looking at extensions that are sufficiently nice, and all the examples I have here on the slide are nice, so 4 cycles, these cliques, paths, and so on, they're all nice. What he showed is that you get this analogous result for, like for the degrees. If the expectation is much bigger than log n, then all the extension counts are close to the expected value. Okay, so the probability that you differ by more than epsilon times the expected value from the expectation that tends to 0. And he proved this for any epsilon bigger than 0 and raised the question, what happens when epsilon tends to 0? And this is something what Matas, Sileikis, and myself revisited last year. So we investigated what happens when epsilon tends to 0. And in some range of the parameters, we determined here the optimal dependence of this result here on epsilon. But let me not dwell on this too much. Here, again, I want to advertise this extreme value perspective. So one thing that is a side product of this proof, or of this paper, where we really took this concentration perspective, is the following. We basically were interested in, okay, so now once we have this concentration result, right now it's natural to get finer behavior. So we want to rescale things here by the square root of the variance. And what we're able to show is that this quantity, right, which looks awfully close already to these things we look at in extreme value theory, that it's always contained in some interval. interval an, bn, where an tends to 0, and here bn is any polynomial function. So imagine it's at least n to the epsilon for any epsilon. And we're able to show that this quantity here always is contained in this interval, okay? With probability tending to 1. So this is not yet quite what we want from the extreme value perspective, but it's kind of a partial result. And let me just mention that to extend this to arbitrary extensions seems to be a little bit tricky, because we know in order to make this statement true, there are examples where you need to take bn much bigger than square root log n, but we also have examples where bn just tends to infinity, where there's no logarithmic factor in there. Okay, so there's some nice work to be done here. So in particular, I think one interesting thing here is to, first of all, there are two levels of difficulty. I think one can ask this question. One is to ask, okay, here we had an and bn, where an tends to 0 and bn tends to infinity. Can we always upgrade this to where a and bn are roughly of the same order of magnitude, modulo some degenerate cases, of course, and then to really address the extreme value theory question. So what happens if from the maximum extension count you subtract off the mean? Can we find a sequence an so this entire expression converges in probability to 1? I think this would be really nice to understand, and I think this is something where some tools and techniques from extreme value theory could be brought into play. And if you're interested in these questions, please have a look at the paper, which is here in arXiv. And thank you for your attention.